Okay, welcome back. If you're just new here, I am working through a series of problems to show you how you can use Python in your introductory physics course. So I'm aiming this at the instructor level, so for calculus-based introductory courses. So these are the kind of things that you can do. I'm not going to focus on the physics too much. I'm going to try to focus on the Python. The playlist for everything will be down below, down that way, somewhere around here. And if you want to check it out. Okay, continuing along. Oh, I do want to say one thing, and I mentioned this every once in a while. I'm going to show you the version of Python that I use. Yes, you can do this by installing Jupyter notebooks and stuff like that, but I've always had a little bit of issue with that, and I like the online version better. When I get to that, remind me to show you what that is. Okay, so I did the magnetic field due to a moving charge. Now I want to do the magnetic field due to a long wire. It's a classic problem in your introductory physics course. You can do this. Basically, we want to find the magnetic field somewhere, let's say here along the x-axis, if this is the xy axis, in the middle of the wire. If you do that, you can break this into small little pieces of current and use the law of Biot and Savart, which is the magnetic field for a point charge, mu naught over 4 pi qv cross r hat over r squared. So in this case, if I have this as my piece right here, then this is the vector r, just to be clear. It's from that piece to the observation location. Now I'm going to make that clear in just a second. And so then r hat is a unit vector in that direction. R squared is the magnitude of that squared. Now, when we deal with electric currents, we really just need to replace QV with the vector I delta L. And that actually only gives the magnetic field due to that piece. So if I want to find the total magnetic field, I have to add up all the pieces. And in the book, you will take the limit as the piece size goes to 0, and you will get this is the answer, because we're going to check this later. This is the magnetic field due to a wire on the middle, and then if you're really close to the wire, you can use this approximate form. We'll check these both out. I'm not going to derive these. I do have a video deriving those, but if you need it later, just let me know. Put a comment down below, and I'll link that in there, but I'll probably forget to do that. Okay, so let's say that we break this into 4 pieces. We're going to break the wire into 4 pieces, and then we're going to assume each piece is a wire that's only at a point. And then I can use this equation, delta B equals mu naught over 4 pi I delta L vector cross r hat over the magnitude of r squared. And that's just the magnetic field due to that one piece. So the first thing we need to do is to find the location of each of these pieces. So let's start down here. If I start right there, if this is a length of L, then this point right down here is negative L over 2. Now, where's that point right there, right? Because I need to shift up a little bit. If this is a length of delta L, and we'll say delta L is going to be equal to L divided by N, right? Where N is the number of pieces I break it into. Then I need to shift this up by delta L over 2, half of a delta L. So that means this very first piece right down here is going to be, I'll call this RP1. It's piece, actually 0. It's called RP0. It's going to be equal to, yes, the vector 0, negative L over 2, plus delta L over 2, 0. Now, I probably... Let's write this as a vector and the magnitude of that. I could write that different ways. But then this will be the vector times the vector 0, 1, 0. So now delta L is a vector. So that's my starting piece. That's the starting location. Now the next piece, RP1, that piece right there, is going to be this piece plus this distance, right? That vector displacement. So all I have to do is add delta L to that. So I can say this is going to be RPO plus 1 times delta L. And then the next one, I'm going to say 2 times delta L. And the next one, and so forth. So I can count this 0, 1, 2, 3, and then I can make all those pieces. Now, like I said, if you put your piece right down here at the bottom, it won't be bad. Especially imagine I have 100, I break this into 100 pieces. If you can do if you can do 4 pieces, you can do 100 pieces. There's no difference, right? And if you do it into 100 pieces, there's really not that big of a difference between the end and the middle. But I'm going to do it the right way because I want to do what's right. Now, in order to plug this in, I need this, I'm going to call this vector right here RO. RO is going to be my observation location. RO is going to be equal to the vector x0, 0, where I'm going to use this 0.05 meters, but I can change that. Now to find R, if I have some R, let's say this is the piece I want right there, RP3, R is going to be RO minus RP3, right? So that's how I find that R. I can do it for any of these. I can just change RP3. Once I have all those pieces, then I can find my R values. Once I have my R values, I can put it into this and find the total magnetic field and then just add it up for all the pieces. Now, I am going to display this at first. I'm going to draw the arrow. Let's just check right here which way this should be. If my current's in the Y direction, then if I put my thumb of my right hand, this is my right hand, in that direction, my fingers curl in the direction of the magnetic field. So you can see it should be in the negative Z direction, which is, that's into the paper. Okay, let's jump over to Python. I'm gonna break this into pieces. I'm gonna calculate the total magnetic field. I can increase the number of pieces, and I can check with my theoretical calculations over here. And we're gonna do that in Python. Okay, so let's jump over here. And I'm reminding myself I was gonna say something about Python. So this is Trinket.io. It uses GlowScript Python, which is also called WebVPython. And in fact, let me just go ahead and show you, let's see, WebVPython. This is the same thing, except that you can, let me just click on a program right here. I want a simple one. Well, this may be simple. And so this has all that you can write your code in a web page. You don't have to install anything, and you can run it. And I think that's awesome. Now, what's different about Trinket right here is that it just has this. One of the things is you can write your code right here and run your output right there. I like that. Number 2, for students, I like Trinket because I can give a link to Trinket, and they can edit it and rerun it, and they don't even have to have an account. They don't have to sign in. They can just go ahead and edit it. They can sign in and save it, but they don't have to. Okay, so there's fewer barriers to entry with Trinket versus GlowScript. So I just typically use Trinket. Also, in some blogging platforms, you can actually embed the Python code from Trinket right into your blog, and I think that's double super awesome. Okay, so let's get started. The first thing I'm going to do is give my magnetic constant, that mu naught over 4 pi. I'm just going to say Km is 1 times 10 to the negative 7. That's mu naught over 4 pi. I'm just going to give this one number. And let's give my other parameters. L equals 1. I equals 0.1. What else do I have? I had, let's see, let's call it XO. That's my observation location, 0.05. Do I have anything else? No? Okay. Now the first thing I'm going to do is break this into 4 pieces. So I'm going to say n equals 4. Now I can find dl is going to be equal to the vector 0, l over n, 0. I got that. Yeah. I'm just trying to think what else I need to do. Okay, let's go ahead and find the starting location. The start R, that first part. I'm going to call this R start is going to be equal to vector 0, negative L over 2 plus mag, I can call this dl dot y divided by 2. I could do mag too. I should do mag. So mag is a built-in function in Python that returns the magnitude of a vector. Now I had to do it that way, and in fact I could have done, actually I could just do this. Plus dl over 2. That looks a little better. And let's just print that out just to check. Print out R start. Okay, so that, if my length is 1, I think that's the right location right there. Okay, let's save this. B due to long wire 3. I think this is the 3rd time I made a mistake before, so I don't want to have multiple things in there. Okay. Now let's do this. N equals 0. Capital N is my number of pieces. Lowercase n is my counter. So I'm going to say while n less than n, do the following. Number 1, find the location of RP. So I'm going to say RP equals R start plus n times DL. So when I start with n equals 0 the first time, R start is going to be at the start. And then the next time it's going to be shifted up 1 DL, then 2 DL, and 3 DL. So it should be fine. And let's print that out just to see if everything looks like it's working. And you got to spell print right. Print RP. Now I'm going to add 1 to n. This is the mistake I make so many times. I forget to add this in there. I get stuck in an infinite loop and time ends. It's terrible. Don't do that. Okay, so run this. There are my 4 locations, negative 0.375. Yeah, everything looks fine. Okay, so now I don't need to print it. I want to put a sphere there, which I don't need, but I'm going to do it. I'm not going to give it a name. I'm just going to put it. So I can say sphere, position equals RP, radius equals 0.01, I think. Let's just leave that as just no color. And there you go. There's my wire. There's my 4 points right there. Everything's fine. Okay, I also need up here my observation location, RO, equals vector XO, not 0, 0, 0. I need this, B equals vector 0, 0, 0. So what I'm going to do is to calculate the magnetic field due to each piece. And to do that, and then add it to the total. But I need to start with a total. So I need to start with some 0 value, and that's what I'm doing right here. Okay, I think we can calculate the magnetic field, so let's do that. I need to find R. So R is going to be RO minus RP, and then I can do it. DB equals KM times the IDL cross R hat. So I can say, cross. Cross is a built-in cross product function in Python. Yay, that's awesome. So cross I times DL and norm R. Norm is a built-in function for the unit vector. So you see how beautiful that is? I can do all this in just one step. This is what makes Python so super awesome. Now I need to divide by the magnitude of R squared. Now I'm going to add that part of the magnetic field to the total. B equals B plus dB, and then I'm going to increment the thing, and then I'm going to go down here and say print B equals B Tesla. Let's calculate B A for the approximate value. I'm looking at my equation over there. It's going to be Km times 2 times I divided by R. Okay, so what's R in this case? It's just going to be XO. Right, because that's how far away I am. And let's calculate the other version, BC, for the one's the approximate, one's the calculated. Km times L times I divided by R times the square root of R squared plus L over 2 squared. Okay, and let's print those. Print BA equals BA Tesla. Print BC equals BC. Oops. Tesla. Okay, let's run it. I didn't save it. Oh, something happened. Cannot raise a vector to a power. I know what I did wrong. Right here, I did R instead of XO. So XO, XO. But it should have done this one. Oh, it didn't get to that line. Okay. Okay, so my numerical version has in the negative z direction. That's good. I have -1 times 10 to the negative 7th. Here I have 4 times 10 to the negative 7th and 3.9 times 10 to the negative 7th. So they don't really agree, but they're not, they're not that bad. And I only have 4 points. Okay, let's change this to 10 points. I mean, if you can do 4, you can do 10. And there's no difference, you see here. And now I have -3 times 10 to the negative 7. It's much closer. Well, let's do, if I can do 10, I can do 100. And there you see, these things agree so well, right? The one that's off is the approximate version, but one is the exact version is a scalar equation, so it doesn't give the vector. This does give the vector. I could draw the arrow there too. I'm not even going to bother with that because I did that before. You could draw arrows for the magnetic field, but I'm not going to do that. Okay, that's a win. But wait, let's show that the functions are the same, that they don't just work here, they work everywhere. So what I want to do is to make a graph of the magnetic field as a function of distance from the wire with these three things. So I need to turn all this into a function. Okay, so that's the first thing I'm going to do. One, I don't actually need to draw these spheres. I'm going to just get rid of that. Let's just delete it. Now I'll leave it there. Okay, so now I don't want to have to redraw those spheres all the time when I make my function. Okay, so let's define this function. Let's say def bn for numerical. And I want to give it a vector observation location. I'm going to call it RR. I don't want to have confusing things. So now I'm going to take all of this stuff and indent it. And now I'm going to see what I don't need. I need that. This is actually going to be equal to, let's just put this as mag RR. So RR, I'm going to give it a vector. Yeah, I'm going to give it a vector value for the location of where I want to find that magnetic field. So XO is just the magnitude of that. After that, everything else works, right? Here I have B, I should call it B temp. That's fine, that's fine, that's fine, temp, temp. And now instead of printing, I'm going to return that value. So I'm going to say return BT. So now I have a function there. Now I'm just going to say instead of printing B, I'm going to call the function Bn. I'm going to put the vector 0.0500. Now these are not going to work, right? Because all these constants are up here in the thing. So actually I'm just going to do this. Let's copy that and put these down here. And no, I want to dedent them. Delete, delete, delete. I need XO equals 0.05. Okay, now let's run it and see if it works. Okay, so it's working. The only thing I've done is I've functionalized the magnetic field calculation where I break it into pieces. And if I want to, I didn't do that the best way or the most elegant way, but if you think about this in terms of this is a course for physics majors or even students taking physics, they may not have had a lot of programming experience. If you try to do something too elegant, they're going to say, "Oh, that's not the way I do it." It doesn't matter if it's not the best way. It matters that they understand everything in there. That's important. Okay, now let's make a graph. So I'm going to say G1 equals graph, X title equals, let's just call it R in meters, and then Y title equals B in Tesla, and let's say width equals 500, height equals 250. Now I'm going to make 3 lines. So I'm going to say Fn equals G curve, color equals color dot blue, label equals numerical. Fa equals G curve, color equals color dot red. You can pick whatever color you want. Label equals calc. Let's just do that. And then let's call this approx. With an R. Okay. And then FC is G curve, color equals color dot green, label equals calc. So I have 3 functions that I can plot. Now down here, I don't want to do this. I have my XO. I'm going to start at let's start at XO equals 0.1, and I'm going to have how far do I want to step to redo everything. So I'm going to say dx is going to be, let's just say 0.01. 0.01. Now, while XO is less than, how far do I want to go? 0.3. I'm just picking something here. And then I say XO equals XO, no, plus dx. I always forget that, so I'll put it in there now. So now in each thing, I want to calculate BN, plot it, calculate BC, plot it, and then calculate. So actually I'm going to put this down here. And then indent the stuff. And then I'm going to put this up here and just copy that. And then this is going to be XO. But I have that function requires a vector. So I think we're good calculating all those things. Increase the x. So before I do that, I want to plot it. So I'm going to say fn.plot XO mag bn. Oh, let's do this. Let's say bnt equals, that way I don't have to call the function twice. Mag bnt, that's temporary. fa.plot XO BA, fc.plot XO BC. And then I'm going to increase x and move on. I don't need these things anymore. Okay, let's see if this thing works. I didn't save it. Okay, looks like it's working. These are right on top of each other, so we can't really see. Let's start over here at 0.0. Let's start over here at 0.07. So 0.07, because it blows up really high right there. You can't really see the difference that much. And let's go to 0.5. Okay, so now you can see the difference. So the blue and the green, oh, I didn't turn on the labels. Did I? Yeah, I did. Okay. So the blue and the green are right on top of each other. They agree really well. Okay. And then as you get further and further away, the approximate value isn't as good because it assumes that the wire is infinitely long, which it's not. Okay. So I'm going to give you this code. I'm going to save it right now. I'm going to give you the code down below. There's going to be a link to the playlist down below for the rest of the series. I think I'm going to do the magnetic field due to a loop because that one is really important. I'm going to show you that that's the same magnetic field pattern as a dipole, and that's what I'll do in my next one. But there you go. Hope you like that. I had fun. Talk to you later.